If you have questions along the way, feel free to interrupt me. So why are we here? Well, one of the things that I want to make sure you guys do is come out with a sense of of knowledge about a variety of different computer systems. So I'd like you to be able to understand after this course, what an operating system is and what its parts are, what the internet as a system is, things like how Ethernet works, just all this good stuff that you really need to know in order to be a good computer scientist, computer engineer, and also things you need to know in order to be able to build systems. Second thing, which is extremely important in systems, in computer systems, is I want you all to be able to understand how to critically analyze a system. So when someone comes up to you and says, hey, I just wrote this mumble system and gives it to you, I want you to be able to look at it and really understand what's interesting about it, what's not, how to respond to when someone says, what do you think about it, in a very intelligent and structured way. I want you guys to get some practice synthesizing your own system design, and I'll talk a little bit more about that later. And the last one here, you see the first two are learn, the second two are practice. Systems is all about practice. I want you guys to get practice presenting and debating your ideas. Systems is a very different type of field in computer science, and there's a lot more practice involved in being able to do systems. And of course, the last thing is next month you guys are going to be doing Philip's course. And Philip is very demanding, and the stuff that you guys learn here is going to serve you quite well in the next month. Questions so far? So one caveat here is to be prepared for something completely different. In systems research, I shouldn't say no categorically, but in general, it's very hard for there to be a wrong or a right. This is very unlike what you might have been used to in the algorithms course. Either an algorithm is order n squared or it's order n, or either it's asymptotically approaches this or asymptotically approaches that. That's very cut and dry. You can prove it. In systems research, it's very different. It's very hard to say my system is right and yours is wrong. And so be prepared for a little bit of that type of feeling. It can feel a little bit fuzzy. The second thing is that it's very important, as I talked about before, that you learn how to critically analyze computer systems. And so here, unlike when you analyze an algorithm where you say, oh, well, here are the things that I need to know, order this, how fast how well it scales, under what conditions it's more applicable than this other algorithm. Here, it's a lot more difficult to say, well, here are the criteria that I'm going to use, or here are the ones that I'm not going to use, because everyone has their own set of criteria. So hopefully by the end of this course, you'll have some idea of what your favorite criteria are and what your favorite way of applying that criteria is. One other thing about systems is there are very few theorems, there are lots of hints, and there's mostly case studies. So unlike, again, most of your previous courses, a lot of what you're going to be seeing here is all about examples. Examples of this system, example of that system, example when this works, example when that doesn't work. But you're going to see very little of, here's a theory that tells you when this thing is going to work or when that thing's going to work. All of this is going to create a lot of perceived fuzziness. It's inevitably at MIT, when you see people taking this course, the first few weeks, sometimes even the first month, people are sitting there thinking, am I really learning anything, or am I really getting it? And part of that is because you read some papers and you say, okay, well, I know how Ethernet now works, so I know how this works. But what you'll realize towards the end of the course is that that's only part of what you're supposed to get here. The other part, which comes through practice, is this analysis, being able to critically analyze systems, being able to debate with someone else properties of systems. That debating, that presenting, that's what's going to come as you go through this course. That's going to come later, and it's not going to come very easily initially. But that's the thing that you have to understand, that that's what your goal should be, to learn that. Anybody can read a paper. If you're smart enough, you can understand every aspect of it. Not everybody can critically analyze, what's important and what isn't, and compare that to another system the same way. So the thing that you're gonna be learning here is how to take this perceived chaos of all these different systems that you're going to look at and turn it into something that represents a little bit more order, a little bit more structure. So that said, participation in this class is everything. I don't know if the TAs have assigned, have they assigned the groups yet, Shai? The,
I don't know. Did Mike sign up last night?
Yeah.
Okay. You guys are going to be working in groups of 2. And the assignments, there's going to be daily reading and writing assignments. And what that's going to culminate in is in every recitation, there's going to be 3 recitation sections in general. Not today, but in general, there's going to be 3. In every recitation section, you're going to have everyone's going to have, each group is going to have to come up with a presentation of yesterday's or the previous day's writing assignment. One is going to be selected. One group is going to be selected. You're probably going to be giving a presentation 2 or 3 times during the month, and the recitation is going to flow that way. The group is going to get up, give their presentation, answering the question or the discussing what they learned about the paper according to the previous day's assignment, and then the rest of the class is going to engage in a discussion, debating their point of view. And the TAs are going to be there to make sure that everyone gets into the whole swing of things. And that's going to be an important part of your grade, as you'll see in a bit. There's going to be a quiz. The quiz is going to cover the readings that you have to do, and it's going to cover anything that comes up in discussion and recitation. The TAs are going to make sure that certain points do get brought up in recitation, so it's important that you're there to discuss them, because in the quiz you might have to actually take a side and present a case. And then there's going to be a final project. Well, this is where the fun begins. So, I'm calling this Survivor AD Uni. There's going to be approximately 17 teams, and there's going to be 1 survivor team. And what you're going to have to do is you're going to have to write and defend either NSF or ARPA computer systems proposal to win. And the people who are going to decide are mostly you, but with some help from the teaching staff. And the team who wins gets fame, fortune, and a handsome reward. I'm working on the handsome reward part, but you definitely will get fame and fortune here. The details are going to be forthcoming. But what's that?
I'll settle for the fame and the fortune.
I'll settle for the details are going to be forthcoming, but the thing to keep in mind is this is one of the reasons it's important to make sure you participate all the way through, because every day is going to be something else that you learn that you can apply, that you're going to be able to apply to the final project that's going to make your team superior to the others.
What is an NSF ARPA system?
Well, NSF, National Science Foundation, and ARPA, they are both government agencies that fund research, and they very frequently put out RFPs, which are requests for proposals. And they'll put out something and say, okay, we want a request for proposal for a teraflop computer. Or they'll say we want a request for proposal for the internet too, or something like that. And they'll give some guidelines. What will happen is researchers around the world will write proposals saying, I propose to do this, to answer this RFP with this type of research. I've done this already that supports that I can do this other thing. I'm going to need this much money to do it, and here's why my system is going to be much better than everybody else's system. And so that's the kind of, it's not going to be, I'm not going to want you to write, some 50-page proposal, but it's going to have a lot of that flavor, and what you write in that is going to have to be something that you can defend and that you can compare and contrast against what other people write.
And the topic is?
Haven't chosen it yet.
Oh, you choose it.
I'm going to choose the topic. I'm going to choose a topic. It's probably going to be based on, I'm going to try to get a feel for what people like, and going to see what's available and try to choose something across those 2 dimensions.
I was thinking we could really send these into NSF and ARP and try to get them all funded and get ourselves on solid ground.
There you go. Why not, right? What do you have to lose? Okay. So any questions so far on this? Okay. So grading. Your daily assignments are going to count 20% of your grade. It's typically going to be a writing assignment. The TAs are going to be grading it on a 5-point scale, giving you feedback. One other thing about the daily assignments is I'd like you to do them on 1 page, front side of 1 page, single-sided 12-point, half-inch margins. I mean, the idea is I don't want a book. I want something that's very clear, concise, that shows that you understand what the topic of discussion is, and something that you can present well to both in writing and to your recitation section.
Are these done in the groups, or these we're all doing these individually?
Actually, originally I thought they probably should be done in the groups, but I think because of this is an opportunity to learn how to write well, not that you don't, but to write well in terms of systems, I think it's better that they be done individually as far as the writing assignments go. Now in recitation, as I mentioned before, there's going to be a team that needs to present. So you're not going to know whether you're the team that's going to be presenting, so you all have to come prepared to present to each recitation. And your participation in that recitation is going to be another 20% of your grade. Now that's going to include, if you're not the team presenting, that includes you being able to ask, you being one to ask questions or to stir up debate. That's going to count. That's very important. The quiz is going to be another 20% of your grade. And then the final project is going to be 40%. That's where it's all going to matter. And this is something you can't cram for. If you don't start day one really understanding what's going on, it's going to be difficult to be the survivor. I forgot to mention the other part. If you don't win, it's going to be shame and agony. So, so you almost win.
You kick people out like
Pardon?
you kick people out on like a daily basis?
No, it's actually going to last over the course of a couple days. There's going to be one big round. That's the way I'm looking at it right now. There's going to be one day when there's an elimination round, and there's a few that are going to be left. And the last day is going to be a lot of scheming and conniving between everybody to figure out, who the survivor is going to be. And there's going to be, some rules that I'm going to set up to make that very interesting.
To make us have to hate each other.
Or not.
There seems to be a big difference between our professors who wear brass rats and the ones who don't.
Oh, okay. Okay. We'll talk about that after class. All right. I'd like everyone to use the AD Uni website. I don't know if you've checked it, but I've posted the class syllabus on there already. I've posted the assignment for today, and I'm going to be posting regularly these lecture notes that I do and anything else that's relevant. There's a systems B-board that I created. I'd like you all to subscribe to it. If you have questions that you want to ask me, that's probably the best place to put them, because that way the whole class can see what the answer is. I encourage you to use it. The TAs are going to use it. Everyone, I hope, is going to use this as a learning medium.
Are you going to post the lecture notes beforehand?
I'm probably not going to post the lecture notes beforehand. I'm probably going to post them afterwards. The day after I lecture.
Okay. I guess like perhaps a lot of people think it's helpful to have them before, because then when you go through the stuff you can annotate your.
Yeah, let me think about that. I've kind of debated back and forth with what's better, and I also find the other side of that is that sometimes people will read them and then fall asleep and say, so I just, we can talk about that later. So just a little bit about me. I've been talking up here, and some of you may have no clue who I am. I've interviewed some of you, so you may remember my voice, and you may remember the bank vault problem that I gave you. Just call me Luis. And I got I'm an MIT guy all the way. I got my master's and bachelor's there, and I got my PhD there in '97. After that, I spent a couple years at McKinsey learning about business, and now I'm working at Photo.net, which is, as many of you know, is is being incubated at Ars Digita. Photo.net was started by Philip, 93, 94. And the ACS, which is what Ars Digita's its business is based on, grew out of Photo.net. I have my website up there. It has all my phone numbers, all my information. So if you ever need to reach me during or after the class, feel free to go there. And I'm giving you a couple of emails here that you can use if you need to reach me directly. Okay. Questions so far? All right. So let's get into systems. So what is a system? For this, just to give credit where credit is due, Salter and Kashok are the two professors who are teaching the systems course at MIT. And this part of the presentation is heavily draws heavily from their teachings. So they define a system as a set of interconnected components as a specified behavior observed at the interface with its environment. So what do all these words mean? Well, when you define a system, one thing that you have to do is say what's in the system and what's out of the system. And the pieces that are in the system are what we call the system components. Everything else is called the environment. The interface is where the interactions happen between the components and the environment. And in particular, a computer system is a system that's intended to store, process, or communicate information. So with that, can someone give me an example of a computer system?
A computer.
Okay.
With the processor and the chips and the stuff.
Okay. Great. Now, what are the components?
Things like a display, a processor, the ribbon cables, and
Okay. Good. Good. Can everybody hear that? Display, the ribbon cables, the disk drive, all the stuff that's in it. Where's the interface?
keyboard and the screen and the network connection.
Keyboard, screen, network connection, mouse pad, things like that. Okay, so from a software point of view, this thing, you can look at this thing as just, it's a box that runs software. That's another valid description of this system. Okay, so where am I going with this? Well, the hardest part about describing a system is deciding what the components actually are. And it's very important that before you discuss any system with someone else, that you make sure that you define what the components are, what the environment, and what the interface is. Now, a couple of metrics that you can use to, or guides that you can use to help you define what the components are, is first, decide what's the purpose of it, what does it accomplish. If you look at the computer as what it is right now, which is basically a projector, really all it is PowerPoint and some video out, right? And who cares about the rest? I don't care if there's a disk drive or if there's just a bunch of memory in there, or if there's a CD-ROM. I mean, that's all irrelevant from that point of view of the system, from its purpose. If its purpose is to do a lot of number crunching and figure out where all these bits are going to be displayed, then I'm interested in the FPU, the floating point processor in it. I'm interested in its computational power, how fast it's going to get these things up there. So make sure that you are very clear. Don't be fuzzy or vague about this, because it'll bite you really hard. Make sure that everyone understands what the purpose of the system is that you're talking about before you start a discussion on it. Second thing is the granularity. It's very easy to look at this as, oh, it's a box, a screen, a hard disk, and so on. But you can actually go deeper than that, right? When you look at you can say, oh, here's a processor. And what about the processor? Well, it's a bunch of layers of silicon. And what about the silicon is made up of all, inside the silicon there's all these gates, and in there's all these electrons floating around, and they all are obeying these quantum laws. And the question is, what level of granularity do you want to study the system? Well, it depends, right? If you're looking at this as, well, as just a box that crunches numbers, who cares about the quantum properties of the electrons running around? But if you're looking at this as, well, here's a system, and let me look at scalability, and let me see how fast I can push it, then you might start thinking about things like thermal qualities and how much power is being used. So make sure that when you're thinking about a system, that you very clearly in your mind know what the purpose and the granularity of it is. When you read these papers about systems, these are a couple things that if you don't understand the components, the environment, the interface, purpose and granularity, you're going to be lost. So when you start reading the paper, if you feel like you don't understand those, I would recommend you just write them out so you can go back to those notes. Make sure you talk to a TA or to someone else immediately to make sure that you're on the same page and you really are starting from the right place. Question?
Is granularity basically the same as abstraction?
Abstraction can be, that's a very good question. Abstraction actually is a way of controlling the granularity. So one example for that's Salzer and that's in the Salzer book is think about if you're looking at a system which is the Earth-Moon system. At one level of granularity, you can abstract that out to be a point point mass, right? If you're looking at the solar system as a whole, you might model it as a point mass. That's an abstraction over it. If you're looking at it as if you're looking at the tidal forces on, or the ocean and the ocean, then maybe looking at it as a point mass isn't really the right way. Maybe you want to actually look at different properties of it that are at a finer granularity. So abstraction is a way of controlling what granularity you want to look at a piece of a system with. Other questions? Okay. Oh, good. Excellent. See, batteries. No one mentioned battery as part of this thing. Uh-huh.
What would be the interface of the Earth-Moon system?
It depends on what the it depends on what the purpose of it is. One of the interfaces you could say are the gravitational forces. Because that's one of the ways it interfaces with the comets that fly around, or with with Mars when Mars gets, But gravitational forces are weak, so they only come into play when something is close. Another thing you may look at the interface is reflectivity, right? So the moon, you get moonlight, right? It interacts with the moon interacts with the Earth in the sense that it reflects sunlight onto the Earth, which has biological effects and so on. So again, it goes back to that, but that's why it's important to are we talking about moonlight or are we talking about gravity? You have to decide what it is that the purpose of the system is, and that'll help you clear out all the other things that aren't key and all the other interfaces that aren't key, and focus on the ones that are key. Other questions?
The relationship between a system's behavior that we choose to observe and its purpose, to me those seem the same thing.
Yeah, it's a matter of deciding what's important and what isn't. There are a lot of behaviors that a system will have that may or may not be important. So this thing here is drawing power from the power grid, right? That may be important if we're talking about how much is the battery, is it going to turn off or not as a system, and how robust is it? But it may be important in that case. It may not be important if I'm just thinking about it as something that I want to number crunch give me an answer in a second, because it's probably not going to turn off in the next second. So
while many behaviors may theoretically be observed, we choose to focus.
Yes.
When those depend upon what we're looking at for the purpose.
That's right. And in fact, that's being able to decide which ones you want to focus on and which ones are important is part of what you need to learn in this course when you learn about a system. And in fact, when you debate each other about systems, you're going to find that some of that debate is going to be around, well, what do I think is important versus what you think is important? And then you're going to have to debate, well, why does my thing that's important, why does it matter, and why does your thing not matter? And it may be that both matter, but it may be that both matter in the context of different purposes. And so you can see how you have to structure your debates around, you have to be coming from the same place before you can even get into a debate about whether some proper interface is better than some other, or some property of a system is better than some other one. Because if you're not agreeing on the purpose, then you're probably going to be comparing apples to oranges. Other questions? Okay. What's all that? Okay.
Hit the click back on it, probably.
Okay. There we go. All right. So why build systems? Now that we have some idea of how we can think about them, there's a variety of reasons why. One of them is speed, and I'm going to give you examples of all these just so that you can get a sense of what the variety of things out there are. One is speed. SETI. Who knows what SETI is? Okay. I don't know if it's running on these computers over here, but SETI has a ton of data. They need someone to crunch it. Their computers are too slow to crunch all of it as it comes in. So what they're doing is they're allowing anyone with a computer hooked up to the internet to do their number crunching for them and find find ET. Biological simulations, as you know, the human genome has been somewhat mostly sequenced. There's a lot of other organisms that have had their genome sequenced. One really interesting thing to do is to be able to use all the computational power there is out there to start simulating what's going to happen when you do this mutation or when you introduce this protein into the system. Very hard to predict. Decryption. A few years ago, there was actually, and I think it's still ongoing, there's some folks who had this contest. It's RSA, I believe. In fact, RSA had a contest where they encrypted some strings, and they used progressively harder and harder encryption, and they have prizes associated with anyone who decrypts these strings. And a while ago, there was some guy who organized a SETI-like system, and the guy said, okay, I'll tell you what, it's a $10,000, I think it's $10,000 prize. If yours is the computer that decrypts it, because he's parallelizing it all out, then I'll split the prize with you. So you can imagine everyone just started running this thing, and eventually it was very quickly decrypted. So speed is one reason. Fault tolerance is another. If you have power outages, if you have bad components, building a system, you can use what you learn in systems to build fault tolerance into a computer. There was a machine a while back. I don't exactly remember the manufacturer. And there's some commercial they had where they took some rifle and just shot it, and it just kept chugging. And this is the kind of machine that if you're a bank, you probably want to have, right? Because this thing isn't going to go down, and if it does go down, you're going to lose a lot of information. So fault tolerance is another reason you want to build. Reliability, and this is a little bit harder to define, but the way I like to think about it is that once the system tells you it's done something, that it actually has done it. And I don't know if you've had this experience, but sometimes here's a system that sometimes doesn't do that. You'll call up a credit card or something and say, have you received my bill? And, oh yes, it's already in the system. And then the next month you get some late notice. Right? That's an unreliable system. Another unreliable system another way that reliability can bite you is you save a file, and then the computer crashes right after that, and then you come back and the file isn't there, or it's corrupted. Right? That's not a reliable system. When the thing says it saved the file, you want to know that it's saved the file, and if the computer crashes, when it comes back up, it's there. Security. There's intentional and unintentional security threats. Who knows what a denial of service attack is? Okay, denial of service attack. One example is why don't you give us an example?
If you can flood a service such that no one who legitimately wants to use it can.
Okay. Can you give us an example of one that's happened in the news over the last 6 months?
You flood DNS servers so no one can find out where machines are on the internet.
Okay, so Microsoft had this problem recently. Microsoft, there was a period of maybe, I think it was a few hours, maybe almost a day, where if you try to go to Microsoft.com, you just couldn't get there. And the servers were up and they were running, they were ready to serve requests. But the problem was that there's a service called DNS, Domain Name Service, that translates Microsoft.com into a numerical address that, we'll learn more about this later, such that a computer can find where this other server is. And that service was disrupted because some hackers started overloading that service with too many requests. And so denial of service means that there's a service that's available and some hacker comes in and does something, either shuts the machine down, floods the machine, does something to prevent anyone else from accessing that service. Now, as much as people like to talk about these sort of outside threats from outside hackers, actually the worst security threats are from inside a company, or from people who have access to the inside. So I actually, while I was at McKinsey, I actually worked for a large telco who had a security product, and they told me that for them, most of their the majority of their clients were concerned about outside threats, but they were most worried about disgruntled employees going in, deleting files, changing data, or someone trying to beat this other guy who was going to get a promotion, sabotage, that kind of thing. And it's all stuff you see in movies, but actually that's how they made their money, was keeping the people on the inside from doing these kinds of things. And they built systems that help a company protect itself from these types of employees. There's also the unintentional, security threats. You're typing stuff, you're borrowing your friend's computer, and you accidentally delete their Windows system directory or their /dev directory or something like that. could be a disaster, and systems can help you protect against that. Availability, anytime, anywhere. If you just have one computer, and it's probably not going to be available anytime, anywhere, especially if it's running some version of Windows. But you can build systems that will help you, even if you're running Windows, to get better anytime, anywhere access. Robustness. This is related somewhat to fault tolerance, but I like to think of robustness as you're a lot more tolerant of input, but you're very strict with output. So if you have some system like the internet, and you throw a bunch of packets on there that are not uninterpretable, that are just kind of bogus, you don't want the whole internet to come down crashing. You want the system to respond very gracefully. Another example is if you pull a hard drive out of a computer. Wouldn't it be great if the computer just kept chugging along, maybe a little bit more slowly, but just as if it's still doing all the stuff? Well, there are systems that do that, called RAIDs. Maintainability. You want to be able to, your system, one of the reasons to build systems is so that you can repair, you can maintain, you can upgrade, and you can enhance the system without bringing it down. And people who love these kinds of systems are banks, financial institutions. Of course, we all love it because we like the internet to be that way, not to come down just because some link gets severed because someone's down in some manhole and cut something. And the last one is scalability. This one is a really, really important point. Ideally, what you want, I'll just draw this very quickly. Ideally, what you want to be the case is that as you increase the load, I'm sorry. Actually, this is performance. So what you want to be the case is that as you increase the load, and I don't know, you can measure this in, number of requests that you can handle, so on. The performance follows a linear path. Sorry, the other way around. If you, it does this kind of thing. As you increase the load, if you have a linear relationship between load and performance. So what that means is if you have say you have a one processor computer that's doing all these steady computations. If you put twice as many on there, you'd love it to be the case that it does them in twice the amount of time, right? If you want it to also be the case that if you put another processor in, that it can handle twice as many in the same amount of time. So this is this linear relationship between performance and load is something that's ideal, that you'd love. Very few systems have anything like this, but what you don't want is what I have up here. What you don't want is the load to decrease exponentially. So you don't want it to be the case that another unit of work slows the system down by half or by a third or by a quarter, because then you very quickly you can load the system up and then it just completely dies. Philip is going to be talking a lot about scalability in his web services. He'll say that the ACS is very scalable, and you'll have to question him a lot about it, especially what you learn in this course. But what he's talking about are things like as you increase the number of hits per second on this web server, right? The web server gracefully, the performance of the web server gracefully decreases. And at some point it'll hit a wall, but what you don't want, what he'll say is that some other services, when you put them up there, that they very quickly decrease into a state where the performance is just losing and you can't use the service. We'll talk a lot more about scalability later. But main thing is, here's a set of reasons why you build systems. But when you're thinking about what's also here is a way of looking at systems, of analyzing systems. So when someone gives you a paper and says, here's my mumble system, right? And what do you think about it? Here are some dimensions that you can use to say what you think about it. You can say, oh, it looks like it would be very reliable, but not very available. There's other reasons that you can add here, but use these as a framework for when you're starting to read these papers and critically analyze them. These are words that anyone in systems will understand and that you should be very fluent in. people may ask you, I may ask you on the quiz, what do you think about how well this system scales, or how well how robust this system is? And I'll expect you to come back and be able to say, this is what I think about it. Questions on these?
Yeah, could you give a few examples of what exactly you mean by availability? And is that like mobile computing, or if you're talking what?
Okay, availability. So availability, one example is, think about the internet, right? You want the internet to be available anytime, anywhere. So is that true? Is it available anytime, anywhere?
More or less.
More or less? Okay, any other opinions?
In this,
Well,
on this
I mean,
continent.
what does anywhere mean in terms of if I don't have a computer in front of me, it's not.
Okay.
Anywhere
Right,
step
if you
beyond
don't have
that.
Okay.
a connection to it.
Okay, if you don't have a connection to it, good. So it's not available. It's not available necessarily anywhere. But if you have wireless, it might be. But not every place is wired up for wireless. Now, if you do have a connection, let's say you have a hard connection to it, is it still available anytime?
Depends if you've got
No. and why not?
If you're really lucky, your ISP could be going down, or network blockages, or you might be able to get to half of the internet, but not the other half.
Right. Okay. Good. So so we're starting to analyze the availability of the internet, and we're finding that, in general, some people feel like it's always available, but there's actually examples of where it isn't. What's a system that's a lot more available in terms of any time, that you expect to be available anytime, than the internet?
The atmosphere.
What's that?
The atmosphere.
The atmosphere. That's built by humans. The telephone system. Good. You expect that to be available anytime. There are some countries where you pick up the phone and you might not get a dial tone. But fortunately for us in the US, for the most part, it's available anytime. What's another service that's available anytime? Electricity. You expect it to be available. You have some power outages. California's not too happy about this stuff right now, but it's that. So what about anywhere? Ham radio. Okay, that's an interesting system. It's a distributed system. There's hams all over the U.S. It's if you're anywhere near, even out in out in less populated places, it's likely there'll be somebody out there who is listening on their ham and will respond. And I've done that, and it's quite fun. What else? Anywhere, an anywhere system. Pardon? GPS. I love that one. Okay, that's the purpose of GPS, is to be an anytime, anywhere system. Right? And unless some magnetic storm from the sun comes over and wipes it out, or some missile goes up, it's probably going to be for all of us. It's going to be anytime, anywhere. We're not going to be going down into the ocean very deep anytime soon. I hope not. So this is the kind of thing. See, we're analyzing systems on the dimension of availability. When you start critically analyzing them, like if you're thinking about the design of GPS, if one of the things that you have to do is have anytime, anywhere access, you have to come up with specs. You have to say, well, what does anywhere mean? Does it mean that does it have to work for planes? Does it have to work just for people around sea level? How much below sea level does it have to work? Obviously you're not going to get this thing to work at the center of the Earth with the current design. So you have to decide what anywhere and anytime means, and then you have to look at the system and decide, when you're reading about it, decide, do I really believe that this system would do this or not? Other questions? Are there any other of these that people want to discuss and go through that are a little vague or okay. So, what makes a system hard to build? Well, in general, it's complexity. And so complexity is again, I'm borrowing from the Salter, etc. book, is lack of understanding of the system's behavior. And the problem with when someone says complexity is, it doesn't mean the same thing here as it did in your last course. Okay, here there's no real absolute way to measure it. So what we look for when we're analyzing how complex a system is we look for symptoms of it. And here's some symptoms. There are others, but I think these are generally the most important. One is a large number of components. Another one, and just because one of these is true doesn't mean it's complex. Usually it has to be a combination. Second one is that there's a large number of interactions between the components. That's a big one. Third one is that there's not very much regularity in it. So that makes it more difficult to, which ties into the next one, it makes it more difficult to describe the system methodically. And a very telltale sign is that it takes more than one person to really understand it. So someone give me an example of a complex system. Pardon?
Genome.
The genome. Okay, genome. There's lots of genes. There's lots of interactions between the genes, actually between the DNA itself and all the proteins in the cell. There is a lot of regularity in the structure, but not in the sequence itself. Oh, I take that back. Actually, there's a lot of regularity in a lot parts of the sequence. You can probably describe DNA pretty methodically, but no one understands it very well. I mean, you can understand. There's a lot of understanding of it, but in general, you can't. I mean, people don't know can't predict what would happen if you change certain genes, mutated them one way or the other. What's in it? Can someone give me an example of a computer system or information system that's complex? Unix. Unix. I think the last one, with the exception of, I don't know if Torvald understands the whole thing. Maybe he does. But it's very hard for any one person to really understand how the whole thing just fits together. Maybe Stallman does. I'll take that back. Okay, let's move on. So where does complexity come from? And one of the things that you may argue when you're designing your system is like, I just won't make it complex. You know, why can't I just not make it complex? Well, it turns out that there's 3 different reasons why it's very hard to design a system that does anything useful that's not complex. And the biggest problem here, which you can conclude from the previous slide, is to really understand something, you need to be able to have predictive power. I don't know if in some of the other classes, if you've studied that in terms of predictive power, but if you don't have predictive power, you don't really understand a system. That's why quantum mechanics is real. The physicists love it because you have huge predictive power over how these wave particles are going to interact and what they're going to do, and it's brought them a lot of joy and satisfaction. What they hate is when they can't predict, what's going to happen at the end of the universe or at the beginning or whatever the current theory is. Same in systems. Systems, folks, we're always looking for ways to predict how systems are going to react and what they're going to do, and along those different dimensions that we saw before. What you're going to find is in general it's very difficult to predict, and the only real way to know what it's going to do is to actually do it. So that's why one thing that you have to be careful of is when someone comes up here and says, oh, I know what my system will do under these conditions. It's either they've done it before, or they're probably, there's some margin of error, and you have to be able to look at that and say, why do you think, is that BS or not? So this is the kind of thing in recitation, especially, that I'm going to expect all of you to do. And one of the big mantras is, when someone makes a prediction about how something's going to react, that's a place that you need to dive in.
So how does that work? We suppose you have like a complete statistical description of your system. Would you say that's predictive or not?
Well, getting a complete statistical description of the system isn't that easy. Like, for example, here's a system.
You could. Then you have some probabilistic.
Yeah, and that's what quantum mechanics. Quantum mechanics is a complete statistical description of the wave properties of types of light.
So we call that predictive or not predictive?
I would call that predictive.
So you could probably argue that a complex system is any system that is too hard to do that with.
Yes. Yes, as soon as you get past the point of being able to predict. Now, you could argue that, you can argue that, well, for some systems, I'm interested in only a small, and the purpose of the system is only to address this subset of issues. And within that subset, I can model it in a way that allows me to predict pretty easily, you know, what the behavior is going to be. And that that's where why you can engineer things, right? You can take a car and you can predict, how, better example, you can take a copier. This is a great example. You can take a copier and you can, for a lot of different aspects of it, you can predict when certain pieces are going to fail. And Xerox actually did this about, I think it was about 10 to 15 years ago. What they did is they took measurements tons of measurements, and then they put all these of copiers, and then they would notice when they would fail and what they would do, and blah, blah, blah. They put this in this huge database and had this program that could run through and look at all of these things very quickly. Then what they did is each copier that they sold after that of that same model, they would have it phone home every night. And the information that it would phone home with was all the measurements that it took that day. And so this big program on the other side would sit there and look at all the measurements and compare them to what it knew, and then come out with some prediction of what part was going to fail when, of the parts that it was monitoring. And so this was great because, I mean, before that, the whole purpose of engineering this system was you wanted, availability was the big thing. You wanted, and reliability. You want this copier to always be available, always be reliable copies. And so people would sit there and try to engineer the parts to work perfectly, and they just got more and more expensive. With this type of approach, now you can get parts that are okay, that aren't that expensive, because even though they fail more often, you'd have a good idea of when they're going to fail. And so the typical story you would hear is like the customer would be there and they get a knock on the door and they say, "Who's this?" It's a Xerox repair guy. And they say, "Well, my copier's working fine." And say, "Won't be working fine tomorrow." And he just replaces the part, and the customer sees no downtime. So in that case, you do have a lot of predictive power over that. But nevertheless, there's still pieces of it that would fail outside of the scope of that. Yes, Shai.
Luis, is there a trade-off between predictive power and the granularity of your system? Because the higher level of abstraction, it seems the more likely you'll be able to make some kind of prediction, and the more you go down into the details, perhaps the less likely you'll be able to control your predictions about what's going on.
I think it varies, and let me give you one example, which I actually have as one of the examples later on here. Take this computer here. If I look at it as just as a processor that takes power and that its speed is related to how much current and what the clock speed is that can pump through this thing, then that's a very abstract point of view. It's very simple, and that relationship tells me, well, the more I clock it, the more power it's going to need, the faster it goes. But if you look down at a lower level of detail, which is what are the thermal properties of this chip? I mean, I don't know. Has anyone here ever overclocked the processor?
Yeah.
Overclocked? Okay. So this, what happened when you overclocked it?
Well, one time I did it, the serial controller got out of sync with the processor, and I couldn't get load.
Okay. So other parts of the system start failing and there's no, abstractly they should all work, right? Because everything's running off the same clock, and so that failed. Has anyone ever had a catastrophic failure?
That was the other time. Some smoke.
And that's, I love it. I have to find this URL. There's some guys who took just so everyone knows, overclocking the processor works at a certain speed, 33 megahertz, 300 megahertz, something like that. And what the processor basically does is one step of work every clock cycle. And so overclocking it means you double the speed at which it does. So when you double the speed, it's going to need more energy to do that. So it consumes more power, more current. But that energy needs to be dissipated because there's resistance for that current to flow through. So it generates heat. So that what these guys did is I don't know, they bought a bunch of bottles of booze, and then they decided, okay, we're going to take our 486, 486 chip, 33 megahertz, and we want to run a version of Quake on it. And Quake usually requires something that's about 10 times more powerful or more to do a good job. So these guys sat there, and they got some liquid nitrogen, and they got this refrigerator, and all this stuff, and they kept pumping this thing and clocking it higher and higher and higher and higher until they actually could play Quake, but it only lasted for a few minutes. And at that point, the whole thing just fried, just like completely fried, even though they had all this cooling on it. But in any case, I hope that addresses the issue that it depends on, that abstracting too much might sometimes not be the right thing if you're trying to predict, what's going to happen to the system, because sometimes the details will come out and bite you. Other questions? Okay. So there's a paper that I've assigned you guys to read, so you'll know what lucky bozos are by tonight or tomorrow. So let me talk about these three origins of complexity. The first is emergent properties. And so these are properties that show up when components are integrated. So one great example is brain cells. Okay, so you have a brain cell. What does it do? It transmits it transmits signals. It modifies the signals. Some of them do fancy things like Fourier transforms. But what happens when you put a lot of them together and when you put them in the right configuration? Well, you get sentience, you get consciousness. Like, how could you ever predict from, if you just looked at this one cell, that's what's going to occur? And in fact, that's one of the things that people who study AI love to think is, oh, if you guys have heard of neural nets, that was an attempt to say, oh, well, let me simulate what one of these cells does. It's got inputs, it has outputs, it has a transfer function that maps the inputs and the outputs. And then let me connect them all, and then let me simulate what happens. And if I can have the right interconnection network, if I have the right transfer function associated, then why shouldn't I get sentience or consciousness out of this thing? And of course, we haven't seen that. I mean, HAL isn't around. HAL 2000 never came to be in 2001, at least not yet. But I mean, how can you predict that kind of thing? Well, you can't. In the same way, anyone who tells you that, oh, I can just take a bunch of components and integrate them, and I'll be able to predict its emergent behavior. Well, you can predict some of them, but there's always going to be some surprise that can come out and bite you if it happens to be the wrong one. What's that? Oh, here it is. So here's the bridge, actually. Let me pass this around. So what happened here? That's a great explanation. Every structure has a set of resonant frequencies, and what that means is that every structure has frequencies that it vibrates at more naturally than others. Think of it like a swing, right? If you're pushing someone on a swing, if the impulse that you give them coincides with just at the point where where they've just stopped and they're starting to go down, then you reinforce, right? And that becomes the resonant frequency is whatever the frequency is that you're giving that impulse at. There are other frequencies which can moderate the action. So, for example, if the person's coming up and you push them right as at the lowest point in their swing, you're going to slow them down. So structures like this bridge, I mean, people said, oh, well, let's design a bridge. Great. Let's put it up here. Great. And each part, worked well and blah, blah, blah. When they put it up there, what they started noticing was that this bridge would sometimes, start doing this kind of thing. And what they realized was that the interaction between the wind and the final structure was such that it was reinforcing these natural frequencies of the bridge. So they just kept reinforcing and reinforcing. And if you actually see the movie, you see there's this car, this one particular day, there's this car and there's this guy trying to walk off the bridge, and the bridge is just going like this. By the way, the bridge out here, the Harvard Bridge, from what I heard, I haven't verified this myself, from what I heard, it actually was the same type of design and had similar types of properties, which is why after this whole accident, they decided to reinforce it and restructure it. Another example that I do know of is the Prudential building, or it's either Prudential or the Hancock. Hancock has this property that it potentially could fall. Actually, not on its broad side, but on its skinny side. And that was something they never checked for because they thought, why would a building, we'll check that it falls this way, but not this way. So they actually, they have a whole floor where apparently they have these huge water jugs, things filled with water, and they have these pumps that kind of pump the water back and forth very quickly to try to compensate for the vibration of the building. So again, this is why it's hard to build systems, because things come up that you think are never going to be an issue, and they do. The third example here is really cool. The computer plus internet plus music plus Napster equals what? Lawsuits. What is RIAA getting really upset? Can you imagine? I mean, this stuff here, there's nothing magic about it, right? Anyone could have written Napster the day out, even before the web came out. FTP has been around for a lot longer than HTTP. If the music industry had been able to predict this, what do you think they would have done if they could have predicted it before HTTP was around?
Build their own system.
What's that?
They would have built their own system.
They would have built, yeah. They would have wanted to kind of get control of this thing before it got away. I mean, it could have been a very different dynamic of what we would have had now as the internet if the music industry, the movie industry, there's a lot of people who've gotten burnt by the internet by simple applications like Napster that have always been possible. The last one here. It won a war, right? I mean, you just get some uranium, some conventional explosives. The trick was this high-tech detonator built, and that system, can release a lot of energy. And as a quick, I love examples, so I hope you guys, this is a systems course. Do you guys know how this detonator interacts with the codes that the president has? So the key here, the hard part about this was you need to compress these pieces of subcritical uranium in a way that's isomorphic, so that they're all compressed equally from each side, so that they all compress into a critical mass that then releases energy. Now the trick is, how do you get that compression how do you get the explosives on the outside to explode at just the right time, so that all the pressure compresses evenly? Because if you don't, then you just get uranium flying out this way or flying out that way, and it's not it doesn't really do much besides what a conventional explosive will do. Well, this is what the guys figured out. And so what the president's codes are is for each nuclear warhead that we have, or each nuclear bomb, there's a set, for each one this is different. So there's codes basically encode what the sequence is of how these things how these little explosives go off so that they compress the uranium the right way. So there's no way that you can actually, if you try to explode this bomb by putting in some other codes, it'll more than likely just blow up harmlessly, because the codes themselves are what make the bomb explode, or what make the conventional explosives compress the uranium uniformly. So this is a pretty foolproof system. So when you see James Bond or someone in one of these movies, and they find they're able to figure out the codes some other way, it's all a bunch of BS, right? It's you don't know what these are, because you use the system only once, and it's a physical system. When it blows up, you either get fission or you get nothing. And again, predictive. None of these are the results of these are. I mean, who could have predicted these? Propagation of effects. This is one of these things where you hear, a tree falls down here, and as a result, the price of oil goes up over there. There's a lot of examples of these. There's changing the design to use a non-standard part. Like, for example, suppose you had your dream house and your architect had designed it, and you decide, oh, I want to have a bigger door because I'm going to be a bigger dude, or I'm going to work out or something. So then so what happens at that point? Well, now you have to redesign the whole house, basically, because now as the doors get bigger, you might have some places where the doors now would jut out into entryways. You might need bigger doorknobs. The hinges might not be able to support the doors, depending on what kind you have. It just kind of propagates throughout the whole design. Another one is larger wheels on a car. If you change the size of a tire on a car, well, now you have to change the size of the trunk where the spare is. You have to make that bigger. Well, that might push the back seats up further, and there might be less leg room, and that might not be safe. So you might have to change increase the length of the car, and it just goes on and on and on. So these are the kinds of things that this propagation of effects makes systems hard to. It's hard to predict when you change one thing exactly how all it's going to propagate. So when you're designing a system, you try to minimize that kind of thing. But again, it's one of those things. If someone says, "Oh, I can just slap one thing in and pull this out and put another thing in, and it'll all just work," you have to question that. You have to make sure they know what they've tried it before at least. And my favorite here is in Episode 4, the original Star Wars. I don't know have you guys all seen the Star Wars? The first one, Episode 4. It was Episode 4, yeah. There's one point where the droids, escape in an escape pod and down onto the planet, and they have the plans for the right. And there's two guys sitting there, and they're about to shoot it down, and the other guy says, "Don't bother. There's no life signs." And 2 episodes later, the Emperor is destroyed, and the rebels win, right? Just from that. So things like that. It's hard to foresee until they actually bite you. Scaling. So this is where the overclocking of the processor. The problem is that as a system scales up in size, speed, or other types of characteristics, you get behaviors that come out that you might not have predicted. Meltdown is one of them. Before Einstein, we didn't think that we didn't know about time dilation and how that interacted with how fast an object went. If you guys have ever read anything about Einstein's theories, you'll know that as the speed of an object increases, the time dilation also increases. Or if the gravitational force on an object, so as an object approaches a black hole, it's time dilation. So time goes slower for them relative to everybody else. And under Newtonian mechanics, what does that matter? But it's actually there's a lot of evidence that this is the case with Einstein's theory. One of the coolest ones here is the mouse. A mouse scaled to the size of an elephant. So have you guys seen some of these movies where the ray you shoot a ray at a mouse or the ant that becomes. So why do you guys have any ideas why wouldn't that work? Why can't the mouse be grown to the size of an elephant?
Heat, for one thing.
Okay, heat. That's an interesting one. Why is heat? Let's go into that one first.
Mass versus surface area.
Okay, so the mass grows as the volume, which is related to the mass, grows as the cube, right, roughly, of the radius, right, of this thing. And what about the surface area? As the square, right? So the ratio of volume to surface area, right, is not the same at all. As this thing goes up, there's less surface area per volume. And what do we know about a mouse's metabolism? Very fast. Right? So they need to give off a lot of heat. What happens if you can't give off the heat to the environment? You become a tasty meal, a hot tasty meal for somebody. So this is a big tasty meal. So what does that tell you about the metabolism of an elephant?
Significantly slower, and they've got a lot more.
Ears. Yeah.
Very good, very good. Why do you think they have these big ears? They need to radiate heat. They can fly. They can fly. They need to radiate heat. These guys, and why don't you see them running a lot? They get in trouble if they get too hot. And now, what was the other? You raised your hand. Okay, you're going to say the same thing. What's another reason that you can't?
Yeah, bones.
Bones. Okay.
It's the cross section, but need to support the volume that's based on.
Good. So the strength of the bones depends on the cross section, right, which grows with the square, right? So, and the volume related to mass grows with the cube, and so at some point the bones are not going to be thick enough to support the structure, so the whole thing will just kind of collapse. So this is a great example of scaling and why anyone who says my thing scales arbitrarily is pulling your leg. Like, don't ever believe it. If Philip comes here and says, my thing just scales arbitrarily, just laugh. And tell him I told you. But that's, I mean, this is another thing that you have to be careful of is when you're building a system, you have to understand, you know, what are the scaling properties of the system? How does it perform as I build it out? The last one is really cool. I just read about this recently, and I don't know if you guys have heard about it. Apparently, someone did an experiment where they were able to supercool atoms and make them exhibit quantum-like properties, quantum mechanical-like properties. So you know that you can take light and mold it into this hologram, right? You don't even need to have this special film anymore. There's some example, I think it's Comdex, where they had they just had this 3D object sort of appear because I'm not quite sure how they did it, but I heard it was really cool. But now they're saying, well, the reason you could do that is because they understood how to bend light in its wave nature. But now that imagine if you could do that with atoms. Well, these guys say that that's one thing that this research will lead to, is being able to just shape something out of atoms that are this way. Not quite sure if it's going to work. Not quite sure, you know, how it's going to come out. But it's just one of these things that this is a scaling down, right? If you bring the temperature down of matter, you get very different properties than you would expect at the temperatures that we all are accustomed to. Okay. So before I get into this, any other questions about complexity and about its role in systems? The takeaways that I want you to get out of this is think about these different types of problems that you have with designing systems. Think about the different types of goals, because in the next lecture we're going to talk about some ways of trying to actually get anything done despite all these problems, and to try to overcome some of these issues so that we can meet some of our goals. When you read your papers too, make sure that you remember these, you know, what the problems are, what the goals are, and try to use that as an early framework to discuss systems. So now getting more into critical thinking about systems. When you read a paper, I mean, there's a lot of ways to read the paper, and I don't mean like by the pool or by, you know, I mean, you know, what do you get out of the paper? And I actually like this framework a lot. And this is a framework that I learned when I was taking the grad version of this class. It was taught by David Gifford. First question is, you need to understand what the problem is that's being solved. For every systems paper you read, you should be able, once you're done with it, you should be able to answer all these questions. What is the problem that's being solved? Very, very clearly, 1 or 2 sentence description. And by the way, the TAs may ask you guys this in recitation. So every systems paper that you read, be prepared to answer all these questions in a 1 or 2 line answer. If you can't answer it in 1 or 2 sentences, then it's probably you don't understand it well enough. Second, what approach is being used? Approach could be something as simple as, well, they're going to build it. And a lot of systems papers, that's actually what they do. They build it. In some papers, they take a theoretical approach. There's some theory in the Ethernet paper that you're going to read about how much you can load the network. But in general, you know, the approaches are they're building it, or they're building a prototype, or they're doing some. That's what they want to do. The experiments that are being performed. So what are they measuring? You know, how are they going to measure the result, the thing that they're building, or the thing that they're doing some theory around? Then what are the key results of the experiments? You can measure a lot of things, but which ones really matter? Which ones really address the problem that's being solved? What conclusions can be drawn? Now this is the interesting part. There's the author of the paper is going to draw some conclusions, and you might draw different conclusions. You might draw extra conclusions, or you might say some of this author's conclusions are BS. Right, but this is something you need to decide for yourself, what conclusions you can draw from that. And finally, what are the next steps? Every systems paper is going to have a set of unanswered questions, and there can be dozens and dozens of them. But what do you think are, at the most, the 3 key next steps to advancing the knowledge of this problem, or to the next problem that arises out of this? And so what I'd like you to do is that every time there's a systems paper, make sure you understand make sure you can answer all of these. There usually would be just one paper, sometimes two, where you actually, or I ask you to go into something a bit more deeply, and that's where you're going to write the one pager. But for the other papers, you don't have to, I don't expect you to sit there and understand every last detail of them. If you understand this much of the other papers, then you probably understand enough of the paper to be able to go back to it if you need to understand it more, or to be able to know whether it's a paper you want to compare, it's a paper that describes a system you want to compare something else to, that kind of thing. Now here's something fun. So apparently using these same kind of mouse arguments, people had, last century, decided that it was no use to try to build large flying machines. And the argument they said, well, is that the weight or mass, as we were talking about before, grows with the cube of the size of this thing as a cube, but the lift, which is based on cross-section of the wing, grows with the square. So, while small things at smaller sizes, it's not a problem, right? Because the things you can make them you can have a really long wingspan, right, or longer wingspan. As you get bigger and bigger, that you'll need so much of a wingspan that it's not going to work. And so for a while, a lot of people just said, you're an idiot if you're trying to build a big flying machine, because this clearly demonstrates that. So the point here is, don't believe everything you read, obviously, even if it seems to make sense. And one thing I'd suggest you do is to take this argument here and decide for yourself why you think it's bogus. And it's, besides the obvious answer, which is, well, we have airplanes. Think about why an airplane can fly, given this argument. So that ends this lecture. What I'd like you to do next is go to the website. On the website, I have an assignment, which is to read. There's let me show you. There's a paper. There's a URL on there to a paper called "Lisp: Good News, Bad News: How to Win Big." Actually, for recitation today, there's one section which I think you'll really love called "The Rise of Worse is Better." And I'd like you to read. It's about 3 pages, three and a quarter pages. I'd like you to read that, and there's a little bit of an assignment there around scheme, which you all have worked for. Come prepared to discuss that in class, and I'm going to be the one who presents this time in class, and I'm also going to be the one who tries to incite some discussion. So I'd like you all to be prepared to discuss that. We're going to have one big recitation. We're going to have one big recitation today, unlike the other days, at 1 o'clock. Okay. So this should take you, 20 minutes to read. Just think about it some. It should be fun, and we'll see you guys at 1.